Well, I think it's time to begin. I am glad to open our first session of the new year, and the first speaker of this year is Vladimir Chetverikov, whom I kindly invite to begin. Volodya, please. And please switch off your microphones.
I'm sorry, we can't hear anything.
I hear nothing.
Yes, I hear nothing too.
Now?
Yes, now it's better.
Hi. You had?
Yes, I'm here.
I can begin.
Yes, please.
I will talk about covariance and multivector pseudosymmetries of differential equations. Okay. Just a moment. No. Consider a system E with independent variables Z, dependent variables V, and consider to find non-local symmetries of the system, a covering is constructed over the system. Namely, one find subsystem, new subsystem with dependent variables W, such that any solution of this system, new system tilde E, is mapped to solution E, and for any solution E, V, there exists some solution tilde E. Then the system tilde E covers the system E. Nu is covering over the equation E. Asymmetry, the new equation tilde E is called non-local symmetries of the equation E. Now let's consider another problem. Let a system S and suppose there is C transformation. It is inverse mapping from the equation S, from the solution of S to the solution of the system of this form. Then phi is a C transformation. The system is covers the system E, and the composition nu and phi is a covariant from S. The fields constitute a pseudosymmetry of S. The system TDE is called a decomposable form of the covariant. Now let's consider example the Laplace equations. Suppose the non-equality holds. Then we have the C transformation phi and the inverse transformation of this form. Decomposable form, it can be proved. The decomposable form is of the form. The set of vector fields GDEq1, GDEq2 is called the pseudosymmetry of the covariant, and the system is. Outline the first part, pseudosymmetries of differential equations. The second part, description of covariance from equations, multivector pseudosymmetries, and examples. References. Covariance of differential equations were introduced by Krasilchik and Vinogradov. Differential substitutions, non-local symmetries, Backlund transformations, and recursion operators were formulated in the language of covariance. Covariance from evolution equation with one special variable were considered by Sokolov. He introduced the notion of pseudosymmetries. The covariance from systems were described in the third work. Finally, multivector fields were used to construct multidimensional pseudosymmetries in the first work. Next, we will use the language of infinite jets. Namely, consider an infinite dimensional space with coordinates x, u, sigma. The total derivatives with respect xi on this space. The infinite prolongation of system S of this form given by is given by infinite set of equations. Then infinite prolongation of system S is a subset of jet space, infinite jet space. The Cartan distribution on the infinite prolongation S is a span of the total derivatives, and this distribution is defined by Cartan forms of this form. C lambda 1 is the Cartan model, and the Ck lambda k is k form, Cartan form, k Cartan k forms. Note that the elements of this module are uniquely determined by this condition. Mappings from infinite prolongation of system S to infinite prolongation system E is a C transformation if three conditions hold. This is the definition of covering of system S to system E. If it can be proved that covering with rank 0 is a C transformation. Let us find the condition for fibers. Fibers of coverings. The total derivative with respect to xi for system 1 and 2 has the form where where the first part is independent of W. Hence, we have these relations, where X is the column of partial derivatives. These conditions 3, are not invariant with respect to C transformations because dy can be converted to linear combinations of total derivatives. Now let's consider invariant version of these conditions. Conditions 4. And column X of vector field satisfying the conditions 4 is called a pseudosymmetry of system S. The relation the relations for and the Jacobi identity imply this relation. Equations 5 are called the Morrow-Cartan equations, the well-known equations. From this equations, it follows that the matrix differential operators d I and A, I and dj and aj commute for any I and j. If AI vanishes for all I, then X is a column of high symmetries. Thus, pseudosymmetry generalize high symmetries. The following two theorem, are generalized. The well-known theorem characterized higher asymmetries. The first theorem describes pseudosymmetry of infinite J space. Where phi A is a vector field, the column vector field of this form. M is a matrix of functions. D is the column of total derivatives. And the second theorem describes high pseudosymmetry, symmetries of system of differential equations of this form. Thus, any pseudosymmetries is the restriction of vector fields of the column of vector fields of this form to S infinity. The matrix phi is the generating matrix of the pseudosymmetry, and phi A is called the evolution pseudosymmetry. Note that infinite prolongation of a system is usually infinite dimensional manifold, and the distribution generated by pseudosymmetry can be not integrable. Therefore, we will give the following definition. We define integrable pseudosymmetries by the following way. A column X of vector fields on infinite prolongation of system S is an integrable pseudosymmetry of system S if X is a pseudosymmetry of S. The vector fields x1, xq generate an involutive distribution of dimension q, and the fitness condition of this form holds. Here, if Is consists of smooth functions of d, u sigma, where sigma is this such type. Example, the fields d v w1 and wq form an integrable pseudosymmetry of system 1, 2. The ring K is the ring of smooth functions of these variables, whereas is the order of system 2. Note that infinite prolongation of system S is usually an infinite dimensional manifold, and a regular and involutive distribution on it can be non-integrable. The finiteness condition allow us to project pseudosymmetry onto a finite dimensional manifold and use the Frobenius theorem. Properties of integrable pseudosymmetries. The distribution generated by the vector fields is integrable. The distribution generated by x1, xq, and the total derivatives is involutive, but is not integrable, because the total derivatives usually is non-integrable vector fields. Any finite dimensional Lie algebra of classical symmetries of a system forms its integrable pseudosymmetry. Any C transformation maps integrable pseudosymmetries into integrable pseudosymmetries. An integrable pseudosymmetries X determines a covering if the fibers of the covering coincide with the maximal integral manifolds of the distribution generated by x1, xq. This is now let's describe coverings from a given system. This is the definition of a regular point of integrable pseudosymmetry. From theorem 3, it follows that any integral pseudosymmetry determines a covering, and any covering from a system determining is determined by an integrable pseudosymmetry. This is algorithm for constructing covering. Let X be an integrable pseudosymmetry of a system S, and let theta be a regular point of X. Step 1, find an integer S such that the coefficients of matrices, these matrices belong to DSK. K is the ring from the definition of integrable pseudosymmetry. Step 2, find common first integrals of x1, xq, and choose new independent variables among the common first integrals and dependent variables, the other common first integrals, and then find functions W1 and WK such that the matrix is non-singular, and this function are coordinates in fibers of covering. The following theorem gives one of differences between pseudosymmetry and symmetry. Namely, any integrable pseudosymmetry determines an integrable distribution, and any basis of this distribution is also integrable pseudosymmetry. Thus, methods for solving defining equations for pseudosymmetries are similar to methods for solving defining equations for higher symmetries. Moreover, to find integrable pseudosymmetry, these methods should be combined with using theorem 4 and the finiteness condition. This is the commutation of pseudosymmetries, and this operation allows us to construct new pseudosymmetries and new coverings. Now let's consider multivector fields, and they should Schouten bracket to simplify the computations of multidimensional pseudosymmetries. We consider Earth's exterior degree of the modular of vector fields on infinite prolongation of S. Elements of this model are called multivector fields on S infinite. An element X is called a homogeneous element of degree R. This is the well-known this is the definition of the well-known Schouten bracket of two multivector fields. And the next slide is properties of Schouten bracket. Antisymmetry of Schouten bracket is Jacobi identity, Poisson identity. The Schouten bracket makes the model of vector fields entirely super algebra. Sorry. Just a moment. Okay. The Schouten bracket makes the model of vector fields entirely super algebra if degree of a homogeneous element is taken to be the integer r minus 1. If X is a pseudosymmetry of system S, then wedge product of the corresponding vector field satisfies the equations, the 6. For some function a, ix, and some multivector z. A multivector field X on infinite prolongation S satisfying the equality 6 is called a multivector pseudosymmetry of system S. If X and A are multivector pseudosymmetries of a system, then wedge product of X and A is also a multivector pseudosymmetry of the system. But this multivector pseudosymmetry can be 0, of course. Let's define interior product of multivector field and P-form by this equality. Then theorem 9 is one more property of Schouten bracket. From theorem 9, it follows that this equality and thus the value of a pseudosymmetry at dl omega is uniquely determined by its value at omega. And this fact allows to compute multivector pseudosymmetry, namely a scalar differential operator of Q Cartan form to Q Cartan form of this form. The set of all scalar differential operators is a non-commutative ring with respect to the composition operation. This set is a left module over this ring, and from theorem 10, it follows that multivector pseudosymmetry X of a system S is uniquely determined by its values as generators of the model of this model. Examples. For the Laplace equation, generators of this model is two series. They are related by the equations of this form. If, for example, X is a multivector pseudosymmetry of this form, then X is a pseudosymmetry of this form. To construct coverings determined by a multivector pseudosymmetry, let's define the Lie derivative of functions along multivector pseudosymmetries by this equality and define a first integral of multi-vector pseudosymmetry of this equality. Then we have this fact. This fact implies this fact can be used to compute coverings determined by multivector pseudosymmetry X. For X from the example 3, the corresponding decomposable form of the covering is this system. The corresponding change of variables is of form. This is C transformation. And example 5. In the situation of example 3, but this equality holds, we have x equals to multivector fields, vector field. The decomposable form of the covering for x is this form, and we obtain the change of variables of this form. Thus, the dimension of a covering can be greater than the degree of the corresponding multivector pseudosymmetry. Finally, let's consider the Kapitsa pendulum, the system with one independent variable t. Only distinction of this system from a mathematical pendulum is that the suspension point can move in the vertical direction. Here, z is a vertical coordinate of the suspension point. U is its vertical velocity. Pi is the generalized momentum. Alpha is the angle. L is the length of pendulum. G is the gravity acceleration. Dot is a derivative with respect to time, the independent variable. This system is equivalent to the system of this form, where R is this function of alpha, where I is this function. Let us compute all the one-dimensional integrable evolution pseudosymmetries of this system. Denote by Fs is a ring of smooth functions depending on this set of variables. The defining equation for pseudosymmetries is of the form where phi is a generating matrix and A phi I phi alpha belong Fs for some S. Three cases are possible. In case one, the column is also a generating matrix of an integrable pseudosymmetry. We use here we use theorem 4. Theorem 4, and the defining equation for this generating matrix is of the form. Suppose psi is a function of the form, then A is of the form. Evolution derivation phi A is of the form. This implies Phi that phi psi A maps Fk to Fs plus K. From the finiteness condition, we obtain that S vanishes. Thus, psi and A are functions of Ti alpha dot alpha only. Finding successful the coefficients at this polynomials in the defining equation 7, we get this solution. Similarly, in the cases 2 and 3, we get the following pseudosymmetries. We obtain 4 series: 1, 2, 3, 4. This pseudosymmetries define the following decomposable forms of system of the system. This is C transformation. Let's now commutation of the obtained pseudosymmetries. A1 and A3 denote the pseudosymmetry corresponding to cases 1 and 3 correspondingly, and let A2 and 4 denote the pseudosymmetry corresponding to case 2. Then we have this relation. Thus, any non-empty subset of the tuple generates an integrable pseudosymmetry of the system of Kapit's pendulum. Thus, we obtain 6 two-dimensional, 4 three-dimensional, and 1 four-dimensional integrable symmetries, and 11 new covariants from the system. For example, the decomposable forms corresponding to the pseudosymmetries of this form are 1, 2, 3, and the corresponding the change of variables. In conclusion, I stress that covariants, pseudosymmetries, and integrable pseudosymmetries are invariant under the group of C transformation and can be used to classify systems with respect to this group. Well, that's all.
Okay, thank you, Volodya. Questions, remarks?
I'm sorry, maybe it is very superficial question which lie on the surface, but you consider vector fields, and there is a theorem that if you have two symmetries, then the commutator of this vector field is also symmetry, yes. But is it possible to formulate it, because we know that Schouten bracket is something like, you can describe it in the language of Haute-Poisson bracket. Can we formulate these statements using the language of Haute-Poisson bracket in the superspace? Okay, maybe, I repeat again, maybe it is very technical. I don't know, I don't understand my question, maybe.
I don't know. I use only Schouten bracket of multivector because we consider distributions and we use Frobenius theorem because vector fields I need I hope to help to find multidimensional pseudosymmetries and multidimensional covariants. This problem is very hard for computation because I use Schouten bracket and this language.
Okay, I'm sorry. My comment is very simple. Maybe it is stupid comment. I just wanted to tell you that everything which is formulated in terms of Schouten bracket, automatically we can translate as a statement about functions and okay, Schouten bracket, it is Haute-Poisson bracket, okay, in the superspace. Maybe this formulation will give it is just technical reformulation. There is nothing interesting in my question except that maybe this point of view will give you another look at what's happening. I'm sorry, just.
I don't know.
Okay, as I understand for Volodya, the language of Schouten brackets is a convenient language to express integrability or invertibility conditions for pseudo symmetries, nothing more, as I understand. Okay, more questions, more remarks?
Vladimir Nikolaevich, two questions, please. The first one, would you show again the slide with references?
Yes, yes, of course. What slide?
The
With
references.
references.
References, okay. Yeah.
Thank you very much. And another question. Am I understand correctly that each covering can be obtained using this pseudosymmetry technique? For example, I have a equation. I would like to construct the covering, and I can recover
Yes,
it by your...
yes, we have a similar defining equation of this equation, of course, and we can use also theorem for because any pseudosymmetry determines distribution, and any basis of the distribution is also integrable, is also a pseudosymmetry. This fact we use in the example of pendulum, the Kapitsa pendulum. We have we consider now phi, and then we consider this generating matrix. This is one, and this step can use to solve this equation. One more method we can use. What this example?
But Volodya, this is true only for finite dimension coverings, yes?
One dimension, of course. One dimension.
In this example, yes, one. But in
this example, yes.
Finite dimensional, it doesn't work for infinite dimensional covering.
Finite dimensional, any finite dimensional covering.
Okay.
So, but this is not applicable to infinite dimensional, or applicable?
Only finite dimensional, and
not straightforwardly. Maybe it can be done, but you should do some amendments. Just I'm afraid that it will not work literally.
Okay, thank you.
I want to say that the dimension of pseudosymmetries X equals the dimension of the fiber of covariance, the rank of the covariance, of course.
Oleg, are you satisfied?
Okay, I need some time to understand.
Okay.
Thank you
More
very much.
questions? More questions? More remarks? No more question? No remarks? Okay, then let us thank our speaker again, and well, we meet in a week next Wednesday. Have a good week and goodbye.